Ah, yes, the Ferris wheel. A quintessential aspect of nearly all amusement parks, carnivals, and entertainment locations. At least those worth their salt. It is hard not to get excited about cotton candy, funnel cake, and snuggling up next to your sweetie as it turns round and round when staring at a Ferris wheel. Most recently, when I looked upon one of these majestic testaments to engineering and science, I thought to myself, how can I make this better? And by better, I am, of course, thinking about scary. Worrisome that I would go there, perhaps, but it did lead me to an interesting mathematics connection to sinusoidal graphs. In the interest of time, I will forfeit the inconsequential details about chainsaws, lighting, pyrotechnics, and the guarantee that patrons will get wet, and of course, the bear. And I'm going to get straight to what really matters, the math. For a structural overview, let's take a look at the basic Ferris wheel. Excellent. Now, when pondering such a device, I thought we could build a large platform that covers the bottom half. Like this. Obviously, it would be more opaque to hide the snakes and whatnot, but you get the idea. This gives us a very nice circle and sets us up to have our X and Y axes placed here as well. And like any good creator of any scary Ferris wheel of doom, I do have to be conscious of the fire exits when it breaks down. To this end, I plan to create vertical ladders to each cart at several locations on the wheel, and this is when my piety sense started tingling. I have a right triangle! Looking at right triangles, we remember all the trigonometric ratios, yes? And the SOHCAHTOA. Looking at the basic right tri, like the one shown here, we would find our angle, that theta there. Find the side opposite the angle. Recall, opposite means far away. And put that over the hypotenuse. While we don't know what size this Ferris wheel is going to be, we do know that it will be 1 unit in length. That is, the radius of the circle is 1 unit. It's a unit circle. Unit circle. That's a great name! That's what we should call it. This is a unit circle. The result of this computation gives us an output of y for any angle that creates theta. Let's repeat this with another angle, like this one. So we find our little angle there, theta. We find the side opposite theta, which is the height, the y. Sine equals opposite of our hypotenuse, which means y over 1, because the hypotenuse is still 1. So y divided by 1 is y equals sine theta. Good. Same. Let's keep repeating this with a whole bunch of these. If we go to the other side, we got the little theta there. Sine of theta equals opposite over hypotenuse. We find the opposite side. That's the y over 1. Hypotenuse is 1. Y equals sine theta. We go to the next one. We got theta, opposite side y over 1, and y equals sine theta. Y equals sine theta. Y equals sine theta. Y equals sine theta. You get it. That does make a pretty cool design. In fact, now that we have a good mathematical model for the Ferris wheel, we can kind of just drop the image altogether to help us see it. There. What an awesome mathematical model. Now let's put some numbers to our unit circle. The values you see here are the angles for our special right triangles, our 30-60-90 and our 45-45-90. You can also see these in 2 different sets of units. The degree, which you are most familiar with, and its equivalent angle in a common unit for angle measures called the radian. Notice pi radians, and yes, that's the same 3.14 pi that you're used to. Pi radians is equivalent to 180 degrees, and all other angles fall into place based on that fact. 90 degrees is half of 180, pi over 2. 360 degrees is 2 times 180, 2 times phi. We'll talk more about radians in the coming lessons, but for now, let's focus on degrees. This lesson is connecting what we know about the trigonometric functions to their corresponding graphs. To this end, let's find our y for all of these given angles with the calculations we just made. At this time, could the operator please stop the tape and create this table and build a nice graph plotting these points. Now that you have had time to try and graph these, your graph hopefully looks a little bit like this. This is a sine graph, often referred to as a wave because, well, it kind of looks like a wave. A few key things to note of. The wave starts at the origin, the point 0, 0. It goes up to a maximum of 1 and down to a minimum of -1, and comes back up to the horizontal axis. This is one wave cycle, or wavelength. We could continue this graph for another cycle, and it would just repeat. This picture gives us 2 wavelengths. Notice the second is identical to the first, so much so that the axis even resets its angle measure. If we continue, we could get a 4th, 5th, 6th, 7th, 8th, 9th, 10th, and on and on and on. This graph will continue infinitely. The domain of the sine wave is all real numbers. This does make logical sense when we actually think about how we generated it. This was generated by traveling around the unit circle, calculating all of the heights as compared to the horizontal axis. That was the opaque box where all the scary stuff resides in our Ferris wheel of doom. And we did this all for the sake of safety. So, it should be no surprise to see that the domain would be all real numbers, since we can keep traveling around and around our unit circle indefinitely. Just like you can travel around and around a Ferris wheel indefinitely. And of course, we keep repeating our measurements because we keep repeating our angles. Furthermore, our height never goes above 1 because the maximum distance from the horizontal of a unit circle, 1 unit circle, is 1 unit. This is how we can create our parent equation for the sinusoidal family. Parent equation? Families? Does this mean the sinusoidal family has an A, H, and K just like all of those other families from long ago? Yes! Great thinking, Charlie. We can manipulate this function just like we did way long ago. And the same parameters are in the same location and do the same stuff to the parent graph. A is still multiplied out front, H still is added and subtracted strictly to the input, and K is still added at the end. Furthermore, A still deals with the vertical stretch, compression, and flip, H still deals with the horizontal shift, and K still deals with the vertical shift. That's pretty cool. Speaking specifically about the A in this wave is also sometimes referred to as the amplitude. The amplitude is the vertical distance from an imaginary line that cuts the graph in half. It is the red dashed line in the picture. And yes, musicians, amplitude does sound a lot like amplifier. Amplifiers, for you non-musicians, make the sound louder in a very basic sense. Sound travels in waves. It can be graphed as a sinusoidal function. And the amplitude of a sine wave tells the loudness of the sound. Amplifiers then simply make the sound waves taller. That's pretty cool. Notice also that the wavelength describes the length of one wave, obviously, but it can be measured from peak to peak, trough to trough, or from any point on the curve to any other point of repetition for one complete cycle. Typically, though, it does get measured peak to peak because it's usually the easiest to find. Also note that for the parent equation, the point h comma k is located at the origin. More generally, the point h comma k lies on the imaginary line that cuts the graph in half. K tells us where that line is, and h tells us what's called the phase shift. It is a fancy way to say horizontal shift. All this struck me while simply looking at a Ferris wheel that I felt needed a little bit of amplification. Oh! All of this we've done is on the sine wave. What about the cosine wave? Challenge extended! Knowing how we derived the sine graph, stemming from the vertical distance to the horizontal, I challenge you to see if you can draw, describe, and create the graphing equation for a cosine graph and compare it to the sine graph. How is it similar? How is it different? Can we make a minor modification to the sine graph to make it a cosine graph? Please have that ready to discuss first thing in the morning the next time we see each other. Good luck.